Welcome everybody back from the coffee break. I hope you have a big cup of coffee and you are ready to do some experiments. As you can see, I'm already in the lab, but before we really put hands on the experiment, I need to tell you a little bit about the details of the experiment. So let me share my screen for this moment. Just a second. Okay, here we go. So my name is Krieger. Together with my colleagues, Johannes Lehmeyer and Alexander Fuchs, I will show you now how you can get fair-ready data from your experiment. And we will also present the tool which we are developing in FAIRmat, which helps you from planning to data collection in your experiments. So this is the situation we are looking at. Not standard experiments, but highly specialized experiments, as you can find in condensed matter physics, material science, optics, and so on, and many other fields also. As you can see in this picture, this shows a specialized ad hoc experimental setup comprising a lot of components and instruments. There's an optical table with lasers, lenses, cameras, detectors, and you can also see electrical measurement equipment like lock-in amplifiers, source measure units, digital multimeters, power supplies, and so on and so on. And with this setup, you want to do an experiment which you have newly conceived, really a new experiment which has never been done before. So you have in mind a measurement protocol which you want to apply. The immediate question is which software to use. Well, there is actually no software which can communicate with all those instruments which you have put together from various vendors and various ages, as you can see in the picture. So what you have to do is you have to sit down and start coding some piece of measurement software. And that takes really, really some time. And it also requires programming skills and special knowledge about device communication. And altogether, this is a high hurdle for implementing new measurement protocols. Okay, now you have programmed some piece of software, and finally, and luckily, it communicates with the devices and stores some data, the data you are interested in. And now you easily turn back to physics because you are interested in this exciting experiment. And maybe you forget documenting the code or documenting the data format because you are already happy with your raw data which you have collected. And maybe there's a few metadata, but maybe not. And altogether, everything is stored in a heterogeneous data format. So that's a problem because maybe you put a lot of time into your program, but nobody else can use it because it's undocumented. And this leads to redundant software development of maybe the same piece of software again and again. And altogether, your data and the software, everything is unfortunately not fair. We follow a new approach here. We develop within FAIRmat a software framework for measurement protocol configuration, not programming. And this configuration helps you from the planning to the data collection phase. This software framework we term configurable application for measurements, experiments, and laboratory systems, or in short, CAMLs. And that's the CAMLs concept. You have your experimental setup, this very specialized collection of devices and components in your lab. And you have the measurement protocol, which you have conceived. And now you simply configure the measurement protocol into CAMLs. And CAMLs takes care on the device communication, on collecting data, and on storing fair-ready data, including raw data and all the metadata the computer knows from the experiment. And that includes the devices used, the settings, also the measurement protocol, and so on and so on. And this data, raw data and metadata, these data are stored in a structured data format. In this case, we opted for HDF5, as Heiko Weber told you already in his talk. Well, this concept really speeds up the innovation cycles in the lab, because this configuration is very fast and you can implement new measurement protocols in just a short time and do the experiment, and then you have maybe a new idea and you can implement a new protocol, and this is really a speedy process. And no programming skills are required. Just to name a few features which we implement or still implementing in Camels, because this is still under development. We develop Camels open source. You can find it on GitHub. We will equip Camels with a setup wizard, which helps you setting up the software and which helps you to start very fast the first measurement. Our goal is that you are ready for the first measurement in less than 30 minutes, including download, installation, and the configuration of devices and measurement protocol. The graphical user interface of Camels does not only just interpret the measurement protocol, but it really generates a standalone Python code, a program, measurement program, which uses the Blue Sky libraries, and you can use this code later on or even share it with colleagues. For the communication with the devices, we use various protocols. Actually, you can use anything which you can put into Python. At the moment, we use PyVisa or Epix as two choices here. And that makes Camels very scalable. You can use it for small experiments, like in this demonstration here, with local and fast device communication using PyVisa. But you can also use Camels in large-scale distributed control systems with instruments distributed in a network, and you can access the instruments via the Epix network protocol. So in total, Camels is very scalable, and you can implement also very complex measurement protocols. But for this demonstration, we have chosen a very simple experiment so that we can show you the experiment from scratch in this tutorial. So for this demo experiment, imagine you have just fabricated a very fancy and new exciting material like that. And this material has an electrical resistance. And maybe you are extremely excited about the temperature dependence of this resistance, R of T. So what do you have to do? Well, you have to measure the resistance of the sample. So you need a voltage source and a current measurement, and you go into the lab and you grab a source measure unit from the shelf and attach this to the sample. Since you are interested in the temperature dependence, you also mount the sample onto a heater, which is connected to a power supply. And of course, you want to measure the temperature, so you install a temperature sensor, which is connected via a temperature controller to the power supply for controlling the temperature. And now we are ready to define the measurement protocol, which is in this experiment quite easy. So the first step is that we set the desired temperature, measurement temperature, in the temperature controller. And then we have to wait for the temperature to become stable. Then we can start the current voltage measurement for determining the resistance of the sample. And after that, we start over and set a new temperature and so on until you are done with the temperatures you are interested in. And this measurement protocol, this can be easily implemented in Camels, and Camels helps you from this planning phase to the data collection of fair-ready data. Okay, and now it's really time to put hands on and demonstrate this experiment, how it looks like in our lab. And for this, I stop my screen sharing and hand over to my colleague, Alex.
Hi, so my name is Alex, and I will quickly demonstrate the experimental setup that we have and show you guys kind of so that you get a feeling for what we use, what does the sample look like, and so that you understand what we measure later on. So let's switch to this camera here. So let's take a wide angle shot of the measurement setup first. So what we have is this sample on the top right here. Then we have our DMM, so our digital multimeter, which will measure the resistance, so get the temperature. And this is our source measure unit, which will measure the current and the voltage and set that and do that. So let's kind of get in close. So you have the sample right here that you can see. It's connected by 2 wires going to these red and black wires on the other side, which then goes to the source measure unit right here into the first channel on the front. This sample is then mounted on a Peltier element that you can see that it's mounted on this chip carrier, and we can heat this chip carrier with these 2 wires. And these go to the back of the source measure unit, so they just go to channel 2 back here. And we can send a current through there, and that way we can heat the sample. But now we of course need to know, okay, what is the temperature of the sample so that we can somehow control the temperature and don't just heat infinitely long. And these are these 2 yellow wires connected to this PT1000 thermistor. So this thermistor changes its resistance depending on the temperature that we have. The DMM here can measure this, and that way we can know the temperature. And of course, we need a PID controller or something that can control the temperature, but this is a software-specific device. We didn't implement this in hardware, and Johannes will show this right now. So now you kind of have an overview of what exactly we will be measuring and what this looks like. And now Johannes is going to show you how in camels we can actually control these devices, measure the temperature, and do this. Exactly.
Okay, hi, thanks. So let me quickly switch to camels first. Okay, now you should see my screen where you see the current UI of our camels program. Here I can set the user and the sample. So we have the FAIRmat demo user and the demo sample here. And then you can see these 4 columns. So we have the devices we want to use. We can set protocols, get here information about running protocols, configure the sequence of the protocol, and then deeper configure the single steps inside the sequence. So let's first start off by adding the devices that we are actually using. So as our digital multimeter, we have the Keithley 2000, which is measuring the thermistor. Then the SMUs, the Keysight B29, and we want a PID controller. Now you can see all these devices are appearing here. And now let's call the Keithley DMM. It's a digital multimeter. And here we can enter a description. Let's say measures the thermistor. Then we can select how it's connected. In this case, we are not using EPICS, but just a local Visa connection, and it's connected to this port. Then we can go over to the next device. Let's recall it as SMU, source measure unit. And here, as a deeper description, the channel 1 measures the IV curves. And our channel 2 of this device is used for heating the sample. Here as well, we are having a local connection via USB. And since we want to use the second channel for heating, we go here and set it as a current source, which is necessary for the Peltier element that we're using. Then we need to configure the PID controller. Let's just have a simple name, PID. I don't think we need a description here. And then as an input channel, we can use the resistance of the digital multimeter, and the output channel would be the current of the channel 2 of the SMU. Now, since the thermistor is just reading resistance and not yet a temperature, we have a conversion function internally for which I just entered the name here. And for the PID values, we can just stay with the default values here for now, at least. Then we add a new protocol. So we get to the next column now. Let's rename it to IV temp, temperature dependent IV measurement. Let's call the file of the protocol the same. And then we can start configuring our sequence. Before we get to the loop, we first initialize our devices. So I add the set channels here. And first we turn on the PID. We give it a set point and we enable the SMU. So we start off with 295 Kelvin and turn on both channels of the SMU. Then we start a for loop for the temperature. So I can just rename it here as temp. And we start at minus 100 millivolts, go up to 100. Sorry, it's not the volts, but it's the temperature. So we start with 295 Kelvin and go up to 310 in 4 steps. So we have nice 5 Kelvin steps. And then inside this loop, the first thing we do is set the new set point for the PID controller. So I just add the value here, the value of this for loop. Then next is waiting until the temperature is actually stable. Not much to configure here. And then we actually do our sweep of the voltage and current. So now we really have these minus 100 millivolts and plus. And let's just do 11 points for this. Now we want to measure with each point the raw value for our temperature, so the resistance of the digital multimeter, then the current value of the PID controller, so the converted temperature, the set point that we had, and then, of course, we measure the current of the SMU, we measure the voltage, and we also want to know which voltage that we set. And for this sweep, we want to define some plots. So let's add just one simple plot. On the x-axis here, we want to have the voltage. And on the y-axis, we add the current that we measure. And let's call this plot IV. The X label would be voltage in volts. And the Y label would be current in amps. And yeah, that's okay. Now we are almost finished. I take now this first initializing step and copy it, paste it into the end, and just switch all the values that we turn on to turn everything off now. Now the protocol should be ready to start. And now let's see what happens when I click on run. So here you can see the PID plot. We're currently going towards the 295 Kelvin. And here is the second, the IV plot. And now the PID controller is going to stabilize the temperature around our set point here. And then the IV measurement should start. Now you can see pretty fast we have our 11 points of current and voltage here, and we're already going for the second temperature, which is now 300 Kelvin. And we have our second sweep. And now we're going to the third value. And you can see this measurement is pretty fast now. And we are almost through. Now getting to our last set point of 310K. And now the measurement is done. Everything was turned off as we configured here. And so now the temperature is dropping back to the temperature that we just have in our lab here. And so I would hand over back to Alex, who will now show you the data file.
Hi, exactly. So now we want to look at this data file that we have. So we would now simply open the space where we said we want to save this file. And you can see the way Johannes named it before, it was IV temp, and we have this file right here. So now you need any viewer that can open an HDF5 file to understand what's in there and to read what's in there. So we can simply open this and then drag and drop. So it's the same thing that Heiko Weber showed before, the same web viewer that we had before. So now if we look at this measurement that we have, we can immediately see that kind of like the title of our measurement is the timestamp that we have. So this was just done a couple minutes ago at 16:29. So this is the measurement that we just did. And as a physicist, the first thing you of course want to do is you want the data, you want this IV dependence of the resistance. So what you would do right away is you jump to the data. So we open the simple sweep, which is what this action was that we named it. And you would probably go to the measured current that we have. You can see the 11 data points that we have. You can also display this as lines. So you can just see these 4 different measurements that we did. You want to go to the voltages that were actually applied. Now you could plot these against each other, investigate this. And normally this is where most measurements would be done. You might also wonder, okay, what was the exact resistance? So what was the temperature? So this is the resistance that we measured with our DMM. These are the temperatures that correspond then to these values. You can see the 4 different temperatures that we had, quite stable. So oftentimes this would be when everything would be finished, you'd save your little TXT or CSV file, this would be in there and you'd have nothing else. But now you might also wonder, okay, I have this file from maybe a colleague. I don't know exactly what he did. What devices did he use? So now you can go into devices. So Camel saves this for you. And you can be like, okay, what were the settings? What is the metadata for my source measure unit that was used? If we open this, you can immediately see it's a pretty long list. I won't go through everything, of course, but you can see that this is the compliances for the different channels. It's the ranges that were set when you set a voltage. It's all kinds of different things, the description of the source measure unit. And the same thing is true for the PID that you have here. So if we go into the PID, you can see we have the different so D, I, and P values that we had. So we just had the default settings of 1. You can see what the maximum output that was allowed was, the minimum value, and so on. You can read up all the things that we input before. You can just read them up if you want to recreate this. So this helps you recreate the experiment if you're like, okay, I also use camels. I just need these PID values to have the same thing and use it. You also have, of course, all instruments, the DMM as well, with all its configurations that we have. Now, this might also not be enough for you. You feel like, okay, I have the data, I know the measurement devices that were used in the settings, but how exactly was this done? There's a million ways you could have measured this. How was it actually done? So you can click on protocol overview here, and this gives you kind of a human readable type format of the sequence that Johannes clicked together. So you can see, okay, we started with the set channels, then which channels were set to which values. We started a loop, we looped over the temperatures, and then set this, and in the end, we turned everything off again. So with this already, you could imagine already just taking camels at your laptop at home and clicking this together the same way. And if you want to go even more in depth, we even have the Python script. So camels then simply writes a Python script and then starts it. And we have the Python script saved here. So if you wanted to go really in depth, wanted to add lines that maybe is strange to configure in a GUI, and measure everything and do different things in between, you can use camels as like a base setup for whatever you have for some devices, and then you can go in depth and add your own code. So you can see this is everything that was done, setting, reading, turning everything off again. And then you can also go into the sample. You can just check, okay, what sample was used, what was prepared and before we measured, what did the user do? So we have fields for the user. If you want to read up, okay, who exactly measured this, if this is relevant as a PI maybe, you can check all of this. But now this isn't completely fair data. This is the fair ready data that was talked about. So everything is labeled, it's described, you can understand it, you know how it was achieved, but it's not some kind of standard. And now I'll pass over to Sherjil, who will show and demonstrate how do I get this HDF5 file actually into NOMAD, actually into some kind of standard, and how can I work with this data then in NOMAD further.